le doy al botón de grabar y muteo y me dejáis de ver y dejo a Irene.
Pues muchas gracias María y a los organizadores por invitarme. Voy a compartir mis slides. ¿Las estáis viendo?
Sí.
Vale, pues entonces, vale, ya lo tengo, empiezo entonces. I will present a search for new physics in proton-proton recorded by the CMS experiment at the CERN LHC. And we use in particular the lepton, either an electron or a muon, and the missing PT final state. And we search for where it's coming from. This is a picture of the CMS experiment. The CMS is a general purpose detector at the LHC. This is an aerial view of the LHC in Geneva. Here is Geneva. You can see the different experiments, and we are located here. CMS is in this in the French side. The detector it has a broad physics program. It has analysis on a standard model, but also in beyond a standard model that is we are going to focus today. I will first present the structure of the detector, how it works. CMS is constructed in layers. So starting from the interaction point, from the middle, I will go layer by layer. First, we have a silicon tracker that is in charge of measure the trajectories of the charged particles and determine the PT, and also the primary vertex. The second layer here in green is the electromagnetic calorimeter, or ECAL, that has a very high granularity, and it measures the energy of the electrons and the photons in the deposits. The next layer is a hadron calorimeter, HCAL, in yellow. It stops the hadrons that travels until the hadron calorimeter, and it measures their energy. All these subdetectors are surrounded by a superconducting solenoid. The solenoid is providing a magnetic field, and it bends the curvature of the charged particles. And due to this curvature, we can determine the charge of the particles and also the transverse momentum. The only particles that all these layers are the muons. So outside the superconducted solenoid, we place the muon system. The muon system has 3 different kind of chambers: the drift tubes, resistive plate chambers, and cathode strip chambers. They are all designed to measure the trajectory, the momentum, and the identification of muons, but it also provides a trigger. And it's here, as Maria was mentioning, where the CIEMAT group has contributed, because it built the part of these DTs, but also in charge of the assembly, the operation, the upgrade, and the readout of the electronics of one part of these DTs. I will now explain you how to reconstruct the main particles of this of analysis, the main objects, starting by the electron. The electron is reconstructed using the information from the tracker here, and the deposit that it makes in the ECAL. With this combination together, it gives a very good electron resolution, a high PT, and a good mass resolution, even for high masses. That is where this analysis is focused. How to reconstruct the muons? Well, the muons, it uses also the information in the tracker, but also the muon chambers. And when the muon has a low PT, the curvature is bent and is very clear. It has a very high PT, a very high momentum, the trajectory is almost a straight line. So we need to enlarge the dimension of the detector. We need a bigger arm. So we introduce muon chambers. With this combination of tracker and muon chamber, we have a muon resolution. Here in this plot is the dependence with the PT. It increased with the PT, but it reached a value of 5%. So it's still a good muon PT resolution. And since we had so much statistics during run 2, we were able for the first time to do a specific study on hypermuons and dedicated a paper to such muons. We had enough of these high PT muons, and we contributed to these studies. Well, how to reconstruct a neutrino? Neutrinos are not detectable by CMS. So the only way to infer their presence is indirectly with the imbalance of the momentum on the transverse plane. The so-called missing transverse momentum, missing PT, is defined as the negative sum of the transverse momentum of all the reconstructed particles in the events. What are the sources of this missing PT? There are all the particles that are not detected by any subdetector, as I say, but it can also come from a potential particle that we don't know beyond a standard model, or also a particle that escapes very close to the beam axis, or escapes through a region of the detector that is not operational. To correct this inefficiency, there are several filters applied to do this cleaning down in this plot, in this distribution, how it corrects the data. And the last object that I will present how to reconstruct with CMS are the jets. The jets are the experimental signatures of the hadronic showers from quarks and gluons. They are, again, combining the information from the tracker, but it also uses the information in all the calorimeters. Then we call B quark to the jets that are originated from heavy flavor decays. These B quarks allow the hadrons to have a longer lifetime, and therefore it travels a bit longer in the detector. Using this information and another information from the B quark jets, we can define a discriminator. The SUSY discriminator is distinguishing between particles less likely B jets on the left in blue, closer to 0, and the discriminator is 1 for the most likely B jet. So that was for the reconstructions of the particles. Now, why looking at this specific channel of one lepton and one neutrino missing PT? Well, this is one of the most clean and sensitive channels to search for physics beyond the standard model. And looking at the high mass, this is one of the simplest realization of the so-called high proofs of new physics, where the effects of the new physics are growing with the square root of S, the center of mass energy of the collisions. And it may appear in the tail of the kinematic distributions. There are many standard model extensions that predict additional heavy gauge boson as the W prime in the sequential standard model. And these bosons are searched as deviation from the standard model prediction, here in blue, in the dilepton mass. It will appear as this red curve. So I will present one by one all the models that we are going to explore with this channel. The first way to explore the channel is in a model independent way. This is using a single beam method on the discriminant variable that is the mass. And we look at the detection of any new particle without specifying the signal shape, so without specifying the model. And this result can be used for reinterpretation, for testing new physics, any new physics that has the signature of lepton+pTmiss. Then the first specific model, the sequential standard model, it predicts the W prime boson. It's a heavy analog of the standard model W boson with the same coupling. We assume the same coupling, and the parameter of interest will be the W prime mass. If we release this constraint on the coupling, we can if we get the result from the width of the resonance and the coupling of the W prime, we can set limit on the ratio of the coupling of W prime and the standard model coupling. Different model that we are going to explore is the split universal extra dimension model. This model predicts another boson that is the Kaluza-Klein partner for each particle, in our case, the Kaluza-Klein partner of the W, as marked here as WKK. In this extra dimension, the radius of the extra dimension is called R. We call it R, and we're gonna set limits on the plane of the inverse of the radius R and the mass, the bulk mass mu. The last resonant model that we are exploring is the R parity violating SUSY model. In this model, there is a mediator, there is a scalar lepton, S tau, that decays into lepton and neutrino. So starting from the model independent limit, we will set limits on the plane of the coupling lambda versus the mass of the S tau. Now to a bit different model, because it's not resonant, it's a non-resonant search, is the search for universal new physics effects in the four fermion contact interaction. This effect can be described by the oblique electroweak parameters, S, T, W, and Y. And we will see in particular how the W oblique parameter induces an effect that grows with the square root of S. And this effect is shown in the propagator of the standard model. So doing the ratio of the modified propagator by W parameter over the standard model propagator, we will get a way to weight the standard model prediction, and this yields the value of a W parameter that makes the background best reproduce the data. And this way we are going to constrain the W parameter. The last model is a Higgs compositeness model. We could consider Higgs composite particle emerging from a strongly interacting sector as a pseudo-Goldstone boson. The W prime boson will be another composite particle, and this sector is characterized by the coupling G and the mass M star. And we're going to set in this plane, G star, M star. How to set limits in this plane? We can do it in three different ways. First, we can be directly sensitive to the spectrum of potential new resonances from UN analysis. And we can do it in two different scenarios, in an SSM scenario where only fermionic couplings are considered, or in an HVT model where the W prime couples not only to fermions, but also to bosons. The second way to set limits is being sensitive to the interference. So it's indirectly exploring the new gauge force via the W parameter. And this allows us to go further in energy. We don't have the kinematical limit. And finally, we can construct with other sectors from than W prime. It will be the Higgs sector. So that was the presentation of all the models. Now I will explain which data are we using. We are using proton-proton collision data from LHC and collected by the CMS experiment. During the run 2, the so-called run 2 are the years 2016, 17, and 18. And the amount of collision produced during these 3 years is the luminosity, and it reached 137 inverse femtobarn. This plot is showing how it was increasing every year during the 3 years of collisions. Then the number of additional interaction in the same or the adjacent batch crossing is the so-called pileup. The pileup is also a bit different between the 3 years. This is the distribution of the mean number of interaction of the pileup. And the Monte Carlo reproduced the pileup, but not exactly as the data, this distribution as for data. Then we correct the Monte Carlo to reproduce exactly this distribution of pileup. We are using some signal samples produced with Monte Carlo for this analysis. We use the Sequential Standard Model W prime signals. This is the heavy analog of the standard model that I already introduced, and it assumes the equal coupling strength and the standard model. But then releasing this coupling strength, we also generate signals with a coupling ratio from 0.01 up to 3. And you can see here how the signal shape changed dramatically with the coupling. So the strategy of this analysis is to search for the signature is 1 lepton plus 1 neutrino where the lepton is either an electron or a muon. And the study is based on a bin likelihood fit between the standard model prediction and the data. The discriminating variable is the transverse mass defined here between the lepton and the missing PT. And there are other processes in the standard model that has the same signature. It has 1 lepton and missing PT. So all these contributions will be taken into account as background. The main and irreducible background is the W, where it decays leptonically, the standard model W. But there are also other processes like the top production. The top decays into both and W. So if one W decays leptonically, we have again the same signature. Same than in the diboson process. If one of the bosons or both is leptonically, then we have the same signature. In the case of the Drell-Yan, if one C boson decays to dilepton, but one of the leptons escapes the detector, escapes the acceptance of the detector, then we will have 1 lepton and missing PT. And finally, a small contribution from QCD, where 1 lepton is produced inside a jet. All these backgrounds are simulated by Carlo samples, and they are all scaled to the run 2 luminosity using their cross sections. And they are corrected with the scale factors that takes into account experimental effects from data. We will use this legend for each of the Monte Carlo samples. We'll go now through the selection, how the strategy of this analysis is following several selection steps in order to minimize the bound and maximize the signal. First, the data is collected using either a electron trigger or a muon trigger with this threshold on PT of the lepton. Then we apply a cut on the lepton PT to be above the threshold of the trigger. And The pseudo rapidity, that is what I'm showing here on the top for the electron channel, on the bottom for the muon channel, in order to be inside the acceptance of the detector. Then we also veto the events that has either an electron or a muon, and we applied dedicated cuts to define the high energy electron ID or the high PT muon ID. They are based on the isolation, on the impact parameters, or the uncertainty of the PT. The next step in the selection is the kinematic cuts. We exploit the two-body decay kinematics in the transverse plane of a massive resonance. A massive resonance should have a balance on the PT because it's produced almost at rest. If you see here the distribution on the left of the ratio of the muon PT over the missing PT, we are going to select the values close to 1 in order to be balanced. And you can see already how if we plot two signal points, they will peak in this region. For the angular distance between the lepton and PT, the delta phi, we are searching for a back-to-back topology. They should be back-to-back in the transverse plane. Then if we cut on the delta phi to be very close to 3, to P, to be back-to-back. The final cuts that we apply, they are in order to reduce the top background. In the top process, there are many jets produced, and some are also BTAC jets. So we use this to cut first on the number of jets. You see the top background that is shown in yellow is mostly at a high number of jets. So we cut for lower than 6 jets, and we cut in the discriminant variable tagging that I already presented in order to cut the most likely BTAC jets. And the remaining top background, what is remain, then is normalized using the data in a control region. I will show now two event displays. They are the high SMT events. So first, in the muon channel, what I'm showing in slide 20, you see here the muon in red, the missing PT is represented as this purple, and you see how it triggers it has signal in the muon chambers. It has a PT of 1.5 TeV and a transverse mass of almost 3 TeV. This is the highest event in 2017. In 2018, in the Electron Channel, I'm showing here the event display. Again, the transverse mass is almost 3 TeV, and you can see in red the deposit on the edge of the electron. Now, with all the strategy of the analysis defined, there is one very important point for the analysis, that is the systematic uncertainties. This is what will determine our limits. So we have all the possible sources included of systematic uncertainties. In this distribution on the right is the transverse mass for the W background in the muon channel. And we plot in different colors all the effect of systematic uncertainties shifted 1 sigma up or 1 sigma minus 1 sigma to see how the transverse mass changes. There are common sources for both channels, in the electron and muon channel. The main sources are coming from the modeling of the background. In the modeling of the background, the K factors that are accounting for higher orders in the Monte Carlo And the PDFs are the two main sources, but there are other sources accounting for the uncertainty in the pileup reweight that I explained, the luminosity, because we are scaling to the luminosity, and also sources related with the missing PT, with jet energy corrections, and the propagation from the uncertainty of the PT is propagated to the missing PT. And all these, the corresponding sources are also applied to the signal. These were the common sources, but there are sources that are particular for each channel. I divide here on the left for the muon channel and on the right for the electron channel. The dominant among the muon channel is the muon PT scale. I will talk about this in more detail together with the trivial scale factors uncertainties. And in the electron channel, the main uncertainty is the energy scale of the electron. So going to the detail of this muon PT scale, we measure this uncertainty with the so-called generalized endpoint method. If there is a bias due to misalignment, we can parameterize it with the parameter kappa. You see in this sketch how rotated or displayed geometry of the detector can infer kappa bias, and this will change the curvature of the muon. The distribution of the curvature is shown on the top right plot for higher, it's starting in -5 to 5, so it's already the high PT, the high PT region. Then the generalized endpoint method, what it does is injects a bias into the Monte Carlo and then minimize the difference between the curvature in this distribution, the curvature between data and Monte Carlo. And we get the value of the bias for each bin of theta and phi in all the geometry. We show here in slide 25 the bias measured for each bin of phi in 3 different colors as a function of eta in the x-axis, and for the 3 different years. You can see how with the years, I mean, it gets better because the bias is smaller. Then this is made for using the PT from the tracker and the muon detector, but it can be made also using is made also using only the tracker PT. And what we see is that is very similar. Then the PT scale effect, this small effect, is at least from the misalignment between the tracker and the muon chambers. Then the uncertainty is derived as a function of the muon PT from an average of multiple maps generated from the original eta and phi bins. And the maximum is found for very high PT at greater than 2 TeV, is a shift on the PT of around 5 or 10%, and is found on the end caps. You could see already that the greatest values were on the end caps. And these studies, we published it also in the dedicated paper to high PT muons, already mentioned. The last thing about the systematic uncertainties, the ones related with the trigger efficiency. The trigger efficiencies are here calculated using orthogonal data sets. These orthogonal data sets are either triggered by missing PT or by electrons, and is shown here in black for Monte Carlo in W sum, and in red for data. On the left plot is as a function of the muon PT, and on the right as a function of eta. Then if we do the ratio of data over Monte Carlo, we get the ratio plot on the bottom on black with this method. And if we use a different method, the tag and probe is here on green. And looking at the differences between these two methods, we can infer the systematic uncertainties to the trigger efficiencies. Now we have all the ends to go to the final distributions. The main distributions of this analysis are the lepton+pT that I'm showing here on the top for the electron and for the muon, and the missing PT on the left, on the bottom row. And so in here together the data, the Monte Carlo, but also two mass points of the signal of the SSM. From here, we could already observe deviation from a standard model, but we don't observe any deviation, but we go to the transfer mass. This is the final transfer mass distribution on the left for the muon, and on the right, on the left for the electron channel, and on the right, muon. We find a good agreement between data and standard model prediction, and these distributions are used as a limit input, as input for the setting. Is what we are going to use to set the limits in all our analysis using the bin likelihood fit. Before going to the limits, I will show the transfer mass distribution split it by charge. This is the case of the muon channel. On the left, selecting a positive muon, and on the right, the negative muon. We could do it since we have a very low muon charge confusion rate, that is the order of 10 to the minus 3 in the highest transverse mass regions. Due to the evolution of the PDFs, the transverse mass distribution is sensitive to the momentum fraction and to the nature of the partons that are involved in the interaction. The rate of W plus over W minus, already measured in the peak of the W, is this value is 1.29. And this value is expected to grow with the mass for higher mass regions in the peak of the W model. Just as an example, extracted by here, the ratio started from 120 GeV is 1.2, and if we go higher to 2 TeV, it already increased to 2.1. So now we move to the statistical analysis. This study is based on a bin likelihood fit, where the observed events are described by a Poisson distribution in each bin, and the uncertainties are modeled with log normal distribution. And we use two approaches. We will use either a multi-bin approach, using information of the shape, or a single bin, where we don't have information of the shape, one bin. We will need the signal efficiency for each channel, what is that I'm showing in this plot as a function of the mass of the W prime, in blue for the muon channel, and in gold for the electron channel. The electron channel is just slightly slower because there are higher threshold on the trigger and offset. The values are around 7 for both cases. And with this, we can set limits on the model independent limit. This is made, as I said, using one single bin. So what we do is we set a bin starting from a threshold on the transverse mass all the way to infinity. You see in this little plot here. With this, we set limits on the electron channel on the left and the muon channel on the right, and the combination of both channels. And the limit is set on section times the branching fraction and times the experimental effects, that are the acceptance and the efficiency. For very high masses, around 3 TeV, we get very sensitive on the order of less than 1 inverse femto. We go now to one specific model, the SSM W prime, where we have the production of one W prime. as a heavy analog of the standard model. We can set limits in each channel. In the electron channel, we observe a limit of 5.4 TeV, muon channel 5.6, and once we combine, the limit mass of the W prime observed is 5.7 TeV. This is the same coupling strength than the standard model, but we could release this constraint of the coupling and set it on the ratio of the coupling of the W prime over the standard model coupling, where 1 the previous scenario. Here we have it split by channels, electron and muon, and we can already exclude for masses of 1 TeV in the ratio of 0.03. The next model is the split UED model, the model of universal extra dimensions, where we have a partner of the W boson called the Kaluza-Klein W boson. In this case, we set limits on the plane of the bulk mass mu versus the inverted radius of the extra dimensions, and dimension r. This limit is for each channel here split and the combination on the right, and it excludes for a mu greater than 2 TeV. Is excluding 1 over r already in 2.8. So here, TeV. If you compare with the exclusion limit of rank 1, that is in red, this line, we have already excluded a bigger portion of this plane. The last resonant model is the R parity violating supersymmetry model, where the mediator is S tau, and the S tau decays into a lepton and a neutrino, and the coupling is called lambda, is different for the case of the electron and the muon, so we have two different limit plots for the two channels, and we set the limit for 4 different cases of the lambda prime coupling, for 4 different values. For this case of lambda prime, this case 0.5, we are including in the lambda of the electron or the muon to be greater than 3.7 or 4.7, 10 to the minus 3 coupling, in the coupling of lambda. Now we move to the non-resonant this is the W oblique electroweak parameter. We already introduced that there is universal new physics effect that in the four-Fermi interaction that can be described by this parameter. And the effect is that the propagator of the standard model is modified. So we can apply this weight to the Monte Carlo prediction. So I will show you now the distribution of the standard model prediction weighted for different values of W prime, of the W parameter. So this is for the very many cases of W parameter. The W value is here on top of each plot. There are negatives, and this is positive values. You can see how the Monte Carlo prediction changes. And what we do is we do a fit between the data and the reweighted Monte Carlo as a function of the W parameter. And we get the best, the W parameter that makes the background best reproduce the data and constrain the W parameter. This is the result for the W parameter. This plot on the left, we are only sensitive to the W parameter, so we in this plane that we have the Y and the W only a straight band. This is the result combining both channels is found to be -12, 10 to the -5, and is consistent with the standard model, that is the black dot, within 2 sigmas. And this new result is reducing the previous bounds from LEP experiment in a factor 10. These bounds are the gray ellipses, and you see how we are now reducing a factor 10. And this is the first experimental measurement of the W oblique parameter using LHC data. Now moving to the Higgs composite scenario, we have this scenario with the coupling G star and a mass of the Higgs composite M star, and we are going to set limits on this plane G star over M star. There are we have three ways to constrain this plane. First, in blue, the two blue are coming from the direct search of W prime. We can do it in the SSM scenario, the W prime couplings only to fermions, on an HVT scenario where the W prime is coupling to fermion and bosons, both. So from these limits in the two scenarios, in the coupling, we can set the limits, we can constrain all this area in blue in the Higgs composite plane. Then the second way to constrain is using an indirect search from the W parameter. We said already that this W parameter allows us to find deviation in the tail, so it allows us to go further in square root of S. So from this relation and the result that I presented in the previous slide of the W parameter, we can go further in mass and constrain here the area in red. And finally, we add this yellow region that is coming from Higgs measurements on the measurements on the cross section of Higgs, and we constrain this area in yellow. With all this together, we can already exclude a composite Higgs of a mass smaller than 3 TeV for the case of the SSM, in the SSM scenario, or a mass of 1 T in the case of the HVT scenario. This is a table that summarizes all the results that I already presented, all the models for each channel, and the observed limit that we put in the different variables for some channel split it and some combination. With this, I will just go to the conclusions. We search for new physics in the lepton, either electron or muon, plus missing PT final state with CMS experiment and using run 2 dataset, that is 137 inverse femtobarn. We didn't find any significant deviation from the standard model expectation. Therefore, we set limits in different ways. We first set limits in a modeling way without using any model, and from this one we derive the R parity violating supersymmetry model that set limits on the plane of the coupling versus the lambda or the mass of the S tau. The way is a direct resonance search. So we search for a resonance in different models, either a sequential standard model with the W prime, on the coupling strength of the W prime, and in a model of extra dimensions. And we set limits in the plane of mu 1/r. The third way to set limits is in an indirect resonance search. We constrain in the electroweak oblique parameter W, and this was the first time that it was made using LHC data. And using the information from these two constraints, the direct and the indirect, we set limits in the Higgs composite scenario on the plane G star versus M star. So that was all. These results are made public in a physics analysis summary. It was presented, as Maria said, 2 days ago in Morion Electroweak. And there is a coming paper publication that is in the last steps from the collaboration review to be sent to journal. On top of this, this will be presented as my main PhD thesis work. Thank you.
Thank you very much, Irene, for a really good seminar and also for the fantastic work. I am sure there are questions. You have several people clapping. I don't know if you can see it. So yeah, if you have a question, please just raise your hand and go ahead. But in the meanwhile, let me break the ice and ask you one while the people get less shy. Well, actually, there is one by Lourdes, so let's start with the one by Lourdes and then I ask mine. Go ahead.
No, Maria, you can ask yours if you want.
No, don't worry, go ahead, go ahead.
Okay. Thank you, Irene. It's very useful. I think for the students, it's a very useful seminar. So thank you. I want to ask if you are considering a tau channel in which maybe the tau is decaying into a lighter lepton, because you are just showing electron muon channel. I don't know if you are.
Yes. So we are not considering this channel, but this channel is made by CMS as well. But the thing is that the tau channel, well, the tau will. I will just show one diagram, Feynman. Okay. A heavier lepton will decay to either electron muon. So if we are considering the I was looking for, oh well, okay, this diagram Feynman. If we are if we have a heavier lepton that decays into muon, then it decays later into muon, then we are again with 1 muon and missing PT. So somehow we are consider the tau channel as let's say as background, because is not introduced as a signal, but is considered the tau will decay into a muon way. So it's at the end it will be the same signature.
It's somehow included. Okay. Thank you.
Irene, and to follow up, and what about the hadronic, just to know, is there a channel, is there a study with the hadronic decays? So tau going to hadron, so you have not leptons in the end.
Yeah, a specific W prime. There is a W to tau and hadrons. I think it's made by CMS. There is also the well, the diboson search. There are more channels. That's for W. Yeah.
Okay, thank you. Then, while more people think their questions, can you show again the interpretation in terms of R parity or the one just before it? I was wondering how this compares with other searches for RPV or for a split UAD. So we do search for this in other models in CMS. So I was wondering how this plot would look if it is possible to compare the limits using the lepton channel with other searches in the SUSY world.
Yeah, no, it's a good question. I don't know, Maria. I don't know the most recent results and how they compare with our, but yeah, then the SUSY group for sure they have more constraints in these models. But I don't know the values and how they are compared. Sure.
Okay, and now there is a question by Juan Pablo.
Hello, Irene. Congratulations. Going there. Okay, so going through the talk, I have seen that the work has been very hard and very interesting, and learning a lot in the process. You are close to the end. One of these could be, for example, that's my question. Do you take a look at the proximity of the lepton to the primary vertex? This lepton considered to be the dotted track of the putative W, and how different it is for your backgrounds, in particular, for example, this tau decay.
Yeah, so you say the lepton to the primary vertex, right?
Yes, impact parameter, for example, or significance, and Z as well, not only in the transverse plane. Thank you.
Yeah, both transverse parameters. We apply a cut in the parameters, in the distance in the XY plane and the distance we actually apply a very restricted cut in this parameter in order to reduce, in the muon channel, in order to reduce any cosmic muons. So we are really not looking at displays, as you say, no? You say displays from the primary, but just cut into very small. Actually, we cut in the C prime, in the C distance. We cut 1 order of magnitude less than the main muon definition in order to remove all the cosmic muons coming from the atmosphere. That was the question, Juan Pablo?
Yes, this was the question. It is around 200 microns, so in the XY, that is roughly 4 sigmas of the primary vertex resolution, probably. Okay. And any idea how is this distribution for example, this tau?
In the case of the tau.
Yes.
Yeah, no, I don't know. No, we look up the distribution of this distribution for our channels, no, and it's very clear how to see. And for high values, the data is over the standard model prediction because you have all the cosmics. No, it's very nice distribution. You find all the cosmics, and we cut it. But yeah, it's a bit of these distributions here too.
Thank you very much.
Thank you.
Okay, so let me go with another while again the rest of the people think. So can you go to slide 24, which I realized how much work was to make this work. It's in the end it's one slide, but I realized this has to have been a tour of force really to get all the muon scale uncertainties and all the muon reconstruction to work. I know that you work on the muon channel, but can you say something about the electron channel that in your previous slide is also marked in orange, right, as one of the leading uncertainties in the electron channel?
Yeah, So it's slightly different, the use of the energy scale in the electron channel, because they, in this channel, they already correct the energy scale. So they obtain in similar, they obtain values now in the energy scale, and then they apply a correction already. So it's different because in the muon channel, what we do is we extract the scale, and from there we introduce a systematic uncertainty. But the electron data is already corrected. So these uncertainty values, they look small, but it's already the uncertainty of the correction. So if you apply the correction and then the uncertainty, you get that this is actually one of the main sources as well. These values are not comparable straight to one channel and the other. It's a bit different, but it's of the order, this correction is the order of 1.5%, if I remember, and then the uncertainty of the correction is 5%, 10% in the up to 10%. This is in energy, as a function of energy, it increases until 10%, and then it's slightly in the NCAP.
Irene,
Sí.
may I ask? Well, congratulations. Exploited a lot this channel. So thinking on this slide, in 3 years from now or so, with run 3, we will have essentially the same statistic. We will have double the statistics. Okay. So what are the areas we should work on to improve the measurement? So thinking ahead, is it worth to repeat this kind of analysis? Are you already thinking or proposing new physics scenarios that should be checked, and now it is we don't have the statistics, but with twice the data, it would be worth to look at? We should work first on the muon-pt scale, or how do you see the future?
Well, working on the muon-pt scale would be good. Definitely, since it's the main source and is the biggest, you can see here. Also in the different colors, now the scale is the pink, so is the biggest. So by seeing the scale of the muons, that it means, for example, better working on the alignment, we could improve this. But yeah, the analysis can be also interpreted with more models. So we double the statistics that next data taken. No? Well, you have already twice the statistics, so you will improve. But there are more channels to explore. So yeah, I think it's worth it to.
But the conditions will be harder. We will have more pileup.
The pileup.
Yeah, and I don't know.
Yeah, maybe more energy. Energy. Yeah, no, well, the pileup will be, I guess for everyone, no, will be a challenge, the challenge of the new data taken. These high pileups and how to deal with it.
Hey, Ignacio.
Okay, thanks, Irene, for the nice seminar. Could you, very nice, could you show the distributions in slide 36 and 37? Could you repeat what was there? And yes, these two sets of distributions.
Okay, so is the distribution of the transverse mass, okay, lepton+pT, of data in black dots already starting of 1 TeV, and the Monte Carlo in pink. And the Monte Carlo, well, standard model Monte Carlo will be for a W parameter of 0, and is, well, in transverse mass distribution that I shown during the analysis. But then if we weight this standard model prediction for different values of the W parameter, that is the parameter that is on top, with this weight is the ratio of the propagator as a function of W. This is the W parameter here. And over the propagator of a standard model propagator. Okay, so this W should use at generation level of the Monte Carlo of the prediction, and is the red, and it changed the shape of the tail, especially in the tail of this distribution.
Okay, and the two slides is just a continuum of parameters.
Yeah.
Okay.
Here, starting from negative values, and then I continue here just to see how
the sensitivity in that tail. Okay, thanks. I understand. And the other question I had is in the positive negative distributions. I guess I mean there are a few events there in the negative muons in the tail. If I look correctly, that was, I think, slide 29. So that is not known. I'm not sure that if I mean, if you look at all it's not significant. You look at all your tests of different models, etc., or what is?
Okay, you mean that in the negative is a bit above the no, in here around.
Yeah.
Yeah, well, it's really no significance. First, okay, there are lines, vertical lines that maybe they're a bit confused because there are lines like errors between the data points, but at the end the data points are only these 3, no? Let's say. And then once you have all together, that is this decision is only this these 2 points. No, it's not significant.
Yeah, it cancels out when you add the 2 charges, no, because the other.
Well, they're not. Yeah, they're under either, but.
Okay, thanks.
Irene, maybe, sorry, this is Begoña. Just to continue with what Ignacio was saying, you have the table of number. Table, yeah, maybe you can show the amount of events.
Yeah, so it's let's say above 2 TeV in transverse mass. We were looking at the muon channel. For data is 21. And if we integrate the background is 21.7. And for 3 TeV, that is higher, there is no more data and all the integrated background is 1 event. So it's covered by the uncertainties.
Okay, thank you to both. Lourdes?
Irene, last question. Sorry. In slide 29, I think. 29. Yes, I mean, maybe it's a stupid question, but I'm a bit surprised by the muon chart already is quite low, and you have a very high PT muons. Do you know how they get that accurate number? Because it's very, very low.
It's well, I can show you also the distribution of here in backup. I had the muon charge misassignment ratio. Okay, so in the y-axis we are showing the charge confusion as a function of the PT, and on the left is for divided for n caps and barrel, and on the right is different charge that is more or less the same. And yeah, indeed, we have much better charge resolution even at low PT, and it worsen a bit, but it only goes to 1/1000 is mistaken. So it's thanks to the muon chambers. No, if we for lower PT we are using only tracker, and only tracker we had enough definition to see the curvature of a muon. Once is very straight, but we use all the muon detector, then we can. It worsen a bit because it's very straight, but we are still very good. So why are we that good? I guess because we have very good muon chambers.
Yay!
Okay, then, okay, last question by Juan Pablo.
Okay, so I was curious about the plot of the page 29 that we have seen it several times already. I was thinking about the resolution of the transverse mass. You probably have taken many times a look into this, and probably it's depending mostly on the resolution on the PT that you saw that it was one of your first plots, right? And that is at worst around at 4%, right? Does it depend on any other thing apart from the resolution on your PT of your lepton?
Well, it's mainly the resolution of the PT, but also the resolution of the missing PT. But yeah, we calculated this resolution as a function of the transverse mass.
Yes, great. Yes.
In order to get the best binning, no? So here we at the end we fix a binning of 70 GeV, but to be in agreement with the resolution, it should be slightly wider at the higher mass region.
At higher masses, for example, it reaches a value of what? 10%?
It's we give it at the 300 GeV, but for the very, very high, like 5 TeV, 7 TeV, 300 GeV of resolution.
Yes, so less than 10%.
Yeah, less than 10%.
Great, that's right.
Okay, I think with that, unless there is an earlier question to close, seems not. So let me just finish. Can you show again slide 39 and slide 40, where we haven't had questions, but I just wanted to remark how impressive it is, okay? And that this is the first time that we do this, and how truly interesting the results are, both in terms of Higgs compositeness and in the W obliqueness. So yeah, congratulations on that to you, to Begoña, to Oscar, to all the analysis team. It's really, and Juan, it's really cool to have this as a result of CMS. So I think we can. It's difficult to clap in the seminars, but consider yourself to have a good ovation. Thank you so much, and also thank you so much to everybody who attended. And as you know, we have these seminars. We try to have them bi-weekly, but now it is Easter, so we will take a little bit of break for the holiday, and we will come back after Easter with new speakers. Eusebio, I don't know if you're saying something.
No.
Okay. Okay, so thank you so much to all, and see you soon.
Thank you, Maria.